Hello everyone and welcome back in our class of Eurocode 7, Geotechnical Design. We'll try to make progress in this program. We are still on chapter 2, Basic of Geotechnical Design. So previously in this chapter, we have talked about this point 1, 2, up to 3 in the previous videos. In this video, I would like to talk about limit state, mainly limit state, okay? This part is very important because this part will govern the design actually. So limit state in the design Eurocode. So as we know, Eurocode stated that for each geotechnical design situation, one should verify that no relevant limit state is exceeded. So there are some limits that we should consider, and those limits should not be, you should not go over the limit. That is the meaning. So in Eurocode 7, the limit we have, of course, you know, ultimate limit state and service limit state. So the ultimate limit state include this one, geotechnical one, which is represented by this geo, and structural limit, structural strength, means the structure itself. For example, if you are in case of foundation, your structure will be the foundation, shallow foundation or deep foundation. This one means equilibrium, and this one is uplift limit state, and this one is about hydraulic failure. Those are the ultimate limit state, and then comes the service limit state. All these limit states should be verified. There are many ways to verify these limit state are not, you didn't exceed this limit state, okay? So the method includes using calculation. So you can use calculation to verify if the limit state you didn't, in your calculation, you didn't exceed limit state. You can use also prescribed measure. That is another method also to verify the limit state. Don't worry, we will explain each of them soon enough. And also you can use experimental model and loading test. You use field loading test. In geotechnical engineering, people do that a lot. So you can use your experimental model in the lab or field loading test to verify this limit state also are not exceeded. And the last one is just by observation. You observe. That's another method to verify the limit state. We will talk about this also very soon. Okay, so anyway, no matter the method you are using, okay, you have to verify that these limit states are respected. So it will include, sorry, I'm just verification of the strength. That will include these two, G1 and SDR, mean structure, geotechnical and structure. That limit is about the strength of the soil or material and the strength of the structure itself. Okay, so that limit state, the verification of that limit state is done by verifying this too. ED should be less than RD, and this ED here means design effect of action. So design effect of action means there are some action like force, for example. Force is loads. So what will be the effect of these actions, these load? Okay. And this RD is design resistance. So action after loading, or I don't know, pushing any force or any load on the structure or on the ground, we need to know the resistance. What are the resistance corresponding to the effect of the force? And then you make sure that the resisting forces or the resistance in general is much higher than the force, the acting forces, or the effect of those acting forces. That is the ultimate limit state. This is not detailed actually. And verification of equilibrium, this one, which is this one. Actually, this equilibrium is also including this uplift limit state. Okay, because for example, I think in the previous video I've talked about the uplift when, for example, you have hydraulic failure, for example, that one also. And this one also, hydraulic failure, uplift, and equilibrium. Maybe all these three can be estimated here. But for the equilibrium one, it is here. So to check, to verify this equilibrium, you need to know that within the forces acting on your structure, your foundation or retaining wall, for example, what are the stabilizing forces and stabilizing forces? Though you can see here, these are the effect of design action from left and right are same. So means in your actions, you will have some action contributing to stabilize your structure, and there are some other actions that are contributing to destabilize your structure. So you have to compare these two. So the equilibrium limit state will be verified by using this. So you see here, ED, but destabilizing forces, and ED, but stabilizing forces. So means, roughly it means the destabilizing forces should be much lower, less than stabilizing forces or effort or the effect of effort or action. Action is like forces, something. That is the meaning, okay? And you will have, this is uplift, and this one, sorry, maybe this one, these last two can be classified here, all of them. So we should verify also uplift. In the last video, I have talked about the hydraulic failure, which is caused by water in the bottom of your excavation. So if water, the effective stress becomes less than pour water pressure, for example, you will have uplifting. It will lift the bottom of your excavation. So we will make sure that the stabilizing forces effect or action or effect of this action are much lower than stabilizing forces effect or effect of action, plus this one RD means the resistance. That is how we verify the uplift limit state UPL. So these are all ultimate limit state. After that, we have also the service limit state, verification of service limit state, we have to check that this ED, we have same definition here. Design effect of actions means the effect of the action, forces or anything acting on the structure, the effect of those forces, of those loads. We have to make sure that these effects are much less than CD, means the limiting value of design effect. The criteria, the serviceability criteria. Okay. Another alternative allowed in some situation is this. So we can check that this RD, same definition as here, the resistance corresponding to the effect, which is divided by this, how to say, this factor, and make sure that it's higher than 3. Another way. Technically, the limit state, this slide is about like somehow summary of all limit state. Okay, so technically this video will end here, but maybe if I end the video here, you will not understand deeply. So for you to understand this in detail and deeply, so we are going to do detailed, to give more detail in this. Okay. Okay. So let's go in detail, discuss more about this limit state. Okay. So this is just what we have talked about in the previous slide. Okay. Nothing new. About this using, we will discuss, give more detail about this point. The method used to verify this, the limit state. The calculation method, we will discuss it in detail in next slide. But let me just bring some more detail about these 3 methods. So this one, the prescribed measure, adoption of this prescribed measure. You know that prescribed measure or prescriptive measure are just traditional and caution design approaches that are used, established, that are using established charts and table. This is just not based actually not using any partial factor, and they are used mainly when there is no possibility to do calculation. So just using design chart and design table. Okay. They are used for issues like durability and local practice, such as footing depth for clay soil. Very traditional way. And then we have this experimental and loading test. Eurocode allow this design based on loading test result, like designing a borehole pipe in clay using total steps and method in anchorage, where in city load test is heavily utilized. And then we have this method just by observing. This method introduced by Eurocode 7 for construction design, allowing adjustment based on real-time performance monitoring. So this one is beneficial for uncertain ground condition, offering flexibility and potential less conservative design. Real-time performance of your structure. Okay. So you know a little bit more about these three. Then this method, calculation method, is maybe the most I don't want to say important, but maybe the one we will give more detail about. So this, in this slide, we will try to discuss more about that method, the calculation method. Okay. This calculation method is illustrated by this graph. So as you can see, we have here actions coming on your structure. For example, you have weight of soil and rock, stress in ground, earth pressure, free water pressure, groundwater pressure, seepage force, dead and imposed load, surcharges, morning forces, and we have removal of load, because when you do excavation, you are removing load. Okay, that is sometimes reducing the effective stress. Okay, you have traffic load, for example, road, and some indirect actions. All these, maybe more, are in this. So you have to consider action, okay, in your calculation. And then ground property, because we are in geotechnical engineering, right? So soil, rock, over material, the ground. What are the property of the ground? Geotechnical property of your ground or rock. You have to consider that in your calculation. And geometrical data also. One geometrical data used is, for example, water level. What is the depth of water level, for example? This is an example, okay? Consider that also in your calculation. Then you have the limiting value for movement, okay? You need to know what is the limitation. What, for example, what is settlement? The amount of settlement allowed, the movement allowed, okay? Then you can choose a calculation model. It can be analytically, semi-empirical, or numerical model using any software. But no matter the method you are using in your calculation model, you have to respect all these: action, ground property, geometrical data, and limitation. Well, and you do your calculation. After this, making the calculation, in your calculation, don't forget to error on the side of safety, and you have to include some simplification also maybe. Then after doing your calculation, you have to check the limit state, both service limit state and ultimate limit state. Okay. And try to check if it respects the movement limitation. And we have here, as we have discussed just in the beginning of this video, we have ultimate limit states like this: equilibrium, so loss of static equilibrium, rupture of excavation, or excessive deformation of structure or the ground, means these two: ultimate limit state of structure and geotechnical point of view. Okay. For this one also, the uplift limit state, which is also another ultimate limit state. We just talked about this one also. And hydraulic failure, like heavy seepage of water. Okay. So for these two, the strength, the verifying the strength of structure in the soil, we will see later that there are three design approaches for this thing to check this. We will discuss these three later by the end of this video. So anyway, as you can see, this calculation method designed by calculation is very interesting. And this is what people are using the most, I think. But don't forget that there are also these just by measuring using design charts and design table, experimental and loading test data, and by observation. Okay. Yeah. This calculation is this one. Okay. Now you know how to check the limit state, all the method for checking the limit state, even if it is roughly explained. You have an idea on how to check this limit state. Then we will go deeply in this limit state. First, we will start with this one. We'll go deeper in how to check this one. Okay. So first we have to know the expression is this one, this equation, or we are saying in equation. This ED, design effect of action. Very simple. It was here already. RG is resistance, the corresponding resistance, design resistance. Okay. And the reference is here. You can check by yourself in the book, the Eurocode. So what we need to know now is how can we get this one? And how can we get this one? The left side one and the right side. Anyway, this expression applies for these two limit states, the structure one and geotechnical one. Okay. Geo one, which is failure or excessive deformation of the ground, in which the strength of soil or rock is significant in providing the resistance. And this one, the structure, is internal failure or excessive deformation of the structure or structure element, in which the strength of the structure material is significant in providing resistance. So for these two, and I think these two are the most important ones, and the one that are giving more, difficulty in calculation. Yeah, anyway, now let's see. I will just put this equation, the inequation here. The expression is here. You have now what you have to check. But how can we verify this? Some people suggested this reference suggested that for the geotechnical one, we can do something like that. But technically it's same. The equation, Eurocode is saying this one has to be much smaller than this one. And the reference is saying that we can use this, calling it degree of utilization, which is ED divided by RD, should be less than 100%. So this is meaning that what is the amount, what is the percentage? Because you have the resistance, this is your power, and what is the capacity of this power you have used? What is the percentage of your total resistance you have used? That's why they are saying this degree of utilization. For example, if you have this is equal to 80%, means you have utilized 80% of the total resistance, the total force. Okay. And this reference, another one, Frank et al. Proposed the design resistance corresponding to design effect of action. They propose this one. Technically, same. This is, as you can see, this just inverse of this. This one, ODF, means over design factor. Okay, this means did you over design your foundation or your structure? So by taking this RD dividing by ED, you have this should be higher than 1. Okay, and as you can see, it's just inverse of this degree of utilization. So now let's talk deeply about this one, ED, design value of the effect of the action. This one, ED, in red here, red color, design effect of the action. How can we get this? So these effects or of the action or any effect of an action, such as bending moment. Bending is the effect of action. You apply load, and this load will cause bending of your pile, for example. So this is effect of action. Shear force in foundation. So these effects are functions of load. Load is action from the structure of any geotechnical action that depend on the ground property and also the geometry of geotechnical structure. So it means that it not only the effect is of course depending on the load and the action, but it also depends on the material, on the ground, for example, ground property. If you have, for example, very strong ground, the effect of the action will not be same. The same action, same force, or same load will not have same effect on two ground having different property, different characteristics. It means that the material property also matters in terms of effect of this action. So if, for example, you apply 100 kilonewton on clay, the effect will not be same as when you apply the same 100 kilonewton on rock. Okay, that's why it's not only about action. We should also consider the ground property and everything. So that's why this one, ED, the design effect of action, because there are the effect and there are the design effect. Effect is about this one, E. Okay, so we have the bending moment, we have the shear force, we have everything, but we need to add some coefficient to these effects, and these coefficients are like here. This we will see later that this is the design approach number 1. You will see later in the following slide. And remember that this one, xk, gamma m divided by gamma m. This one is, this term is introduced in the expression. It's introducing the influence of the ground property, such as strength, weight, density, geotechnical action, let's say you have pressure, geotechnical resistance, bearing capacity, bearing pressure, for example. But anyway, this one, the F representative, this one, F, means representative or characteristic value of action or the effect of action. Okay, F is the action or representative action. Means you have two choices. You can use F rep or F this K, and the characteristic value of any action means this one. In case it is characteristic value is primary representative value. An action, particularly if it is variable action, for example, in the previous video, we have talked about variable action, may have over representative value. For example, when the variable structure action are combined. So this primary representative value is the FK. Okay, so you can use both F representative or F characteristic, the representative force or characteristic force. And this one, gamma F, is partial factor for action or effect of the action. So the reason is very simple. The reason why we use this is very simple. It just to minimize or maximize some force or some effect. Okay. This is the reason why these factors are used. So you have two choices. You can use the action itself, or you can use the effect of the action. In case you use the action or force, that one is this one, representative force, representative action. Okay. So in that case, you have to use this partial factor, kind of safety factor, something like that, multiply it by the action, the force. But in case you use the effect of action, in that case, this gamma is not gamma F, but gamma E, gamma effect. F is standing like for force, E is standing for effect. But anyway, you have two choices. You use the force or you use the effect of the force. Next, and this one, actually, the effect of the gamma F is used where the factor applied to an action. This is what I was saying. And the gamma E factor apply for the effect of the action. The next is this one, XK. This one is characteristic value of material, ground property. Okay, the ground property. For example, unit weight or frictional angle. Okay, so this characteristic is then divided by this another partial factor, this partial factor for material property. Okay, so if you have let's say a high property, the material property that is contributing for the stability, for example, you can minimize it by dividing it with this one, this partial factor. This is just for safety. Okay, and the last one is this one. This A is the design value of geometrical property. Example, the depth of the water table. We have to consider that. So in this expression, you see three main part. This first part is about the action or the effect of action. We use this coefficient for that. Okay. The middle one is about the material property, the soil property, the ground property. Okay, that one also is divided by this partial factor to minimize this. Here is maximizing, maybe here is minimizing. But we will discuss more about these factors, these partial factors later. And the third one, we have geometrical property. For example, here we have example here, the water table. So three part. Okay, this is how we express this effect of design action. Yeah. So you know why the ground property can influence the effect. Okay, I explained just now the beginning of this slide. Same action, same load will not have same effect on clay and rock, for example. Yeah, that's why we need material property. And the water table will definitely influence the effect of any action in the ground. Okay, I will just put all this here because we will use it again. This is from the previous slide. Now, let's see deeply about this one, the resistance one. Design value of resistance, this one. Okay, so design value, when you hear design value, it means the resistance multiplied by partial factor, by using partial factor for safety. Okay, because you will have the resistance, and after using some partial factor to multiply or divide, technically it's safe, you will have the design resistance corresponding to the forces. So this design resistance in general, it will be function of ground, a function of the applied force, applied load, applied action, if you want. As we see, this gamma F multiplied by F representative here. Okay, it will be also function of the ground strength, which is the middle part, and also function of the geometrical quantity, this one. Safe. But in this case, to obtain this RD, the partial factor may be applied either on the ground property, means this one, or the resistance. Okay, we can do this one. For this is an example. So check here, the difference is here. You have here E and you have here R. For the effect of action, we are taking the actual or the calculated effect that we multiply them by some partial factor. But here, it's like we are taking the resistance, total resistance, multiplying by some effect. Okay, some partial factor, sorry. Multiplying the resistance multiplied by some partial factor. So we can have this form, or sorry, this also design approach one applied generally for geotechnical resistance. We can have also another one. Instead of using this this partial factor gamma M, the material. In this case, we don't use it. We use this one, gamma R. This gamma R is partial factor for resistance of the ground. Okay, so we have two ways, but no matter which one we use, remember that this one should be the R, the resistance. So this one also, design approach. This expression is applied to design resistance of pile and anchor only. Okay, this one. So now we have expression of the design effect and the two expression for the design resistance. Okay, design effect of action and design resistance. So this first expression of the design resistance, in this expression, the design value of the resistance is obtained by multiplying the partial factor. The gamma m should be higher than 1. This gamma m. Okay, to minimize the strength of the soil, just for safety. So this one is to the characteristic value of the ground strength. Means, for example, this xk will be, for example, the x can be C, cohesion, can be phi, means internal friction, or can be Cu in the undrained situation. This is drained situation, this one is undrained situation. Okay, the x here means geotechnical parameter of soil. Okay, it can be C, cohesion, when the situation is drained situation. It can be frictional angle, prime, effective one. Okay, and it can be Cu also. But this coefficient, the partial factor gamma m, should be higher than 1, so that we minimize the strength of the ground. Okay, so if this partial factor play a role, if the action on the ground play a role in resistance, then design value of action means this action, because it doesn't mean that anytime you have this only when the action is contributing to the resistance. Okay, for example, if you have retaining wall, from each side you have ground. One side is stabilizing the ground, maybe another side will be destabilizing the retaining wall. For some action are contributing to stabilize your structure. So if any action is playing that kind of role, then the design value of the action, this one, are introduced in the calculation of the total resistance. It doesn't mean that you have it anytime you are doing. Sometimes you don't have any action that is contributing to resistance. Okay, but in case you have a action that is contributing to the resistance, you have to use this also. So sometimes the resistance in the ground includes a contribution from the representative action, as I was saying, such in the case of the spread foundation, subjective to inclined load. Now let's talk to the second one, the second expression. In the second expression, the design value of the resistance is obtained by applying the partial factor, the gamma R, this gamma R. It should be higher than 1 so that we can minimize the resistance for safety. Okay, so that will be to the resistance will be applied to the resistance obtained using characteristic value of the ground strength parameter. And we should note here that the value, the term xk here in the material property has been used only because this gamma m is 1, and this one is 1. So we use this. If we have also any action, any force, or any load that is playing the role in the resistance, the force or action that contribute to the resistance, in that case, the design value of the action, this value, this one, are introduced in the calculation of the resistance RD. But with the gamma G means the permanent action. If the action is permanent, then the partial factor of that action will be 1. But if the action is permanent action but is favorable action, then we will multiply it by 1.3. So in that case, if we have this as 1, then we can say that the equation, this second equation, will become this one. Only if this is 1. Okay. So we have now all the equations here. Remember, this one is for the effect, the action's effect, the loading effect or the force effect. And these are for the resistance. Okay. So here is how it works. We want to verify, we want to check if any limit state is respected. Okay. So for verifying this limit state, this one, you go first with the action. Characteristic action. I think I've talked about this before. If you can use characteristic action or you can use representative action. Okay. In case you are using characteristic action, you have to use this partial factor to multiply it to minimize or maximize the effect, the action. And you can use this when you are using representative action. So F representative, you use this, the partial factor gamma F, which is in our case here. You can see this red one. Okay, the red is this color. Then after using that, you can have the design action FD. So design action is representative action multiplied by partial factor of this action. So means this is in the red, the thing we have here in red color is design action. Okay. Or instead of using these partial factors, you can directly use the effect of the action. So design effect of action, ED. In that case, you multiply it by this gamma E, as we explained here before. Gamma F is for the action, but gamma E is for the effect of the action. So you have two choices. You use action. In that case, you multiply the action by a this partial factor, or you use the effect of the action, means bending moment, for example, or the sharing force, the sharing in the ground, something like that. In that case, you have to use this gamma E, means the partial factor of the effect, force effect. Okay, this is for the action. And you have for the material here, this right side for the material. So you have characteristic material property xk, okay, that will give you the strength. I have explained this before. It can be the cohesion, the x can be replaced by cohesion, it can be replaced by internal friction angle, okay, or also the undrained shear strength, the cu also, okay. Then you multiply this by this gamma m here. So this blue part means xk divided by gamma m will give you the design material property, okay. Characteristic material property multiplied by the partial factor gamma m will give you the design material property. Means that you take the material property, you put just safety factor, merging factor, that's all. That is the meaning of design material property. Because we have material property, the actual one, but we have the one we will use for design. That one will be the one obtained after multiplying by the partial factor, okay. That is the meaning. Or you can go also, instead of using this, the material property, you can use directly the resistance, design resistance, because what is resisting is the material. For example, the soil is resisting, for example, okay, but there are some action also contributing for the resistance. But anyway, you can use this gamma R instead of gamma M. But this, if you want to use gamma R, that gamma R is used here directly. Design resistance. To obtain design resistance, multiply here. I think the meaning here is design action. You have two choices for each, for the action and for the material property. You can multiply the representative action by this gamma F, or multiply the design action by this one. Here also same, design material property multiplied by gamma R, this one, for example. And the last one, the one in yellow, here in the middle here, you have the geometrical parameter. You have nominal dimension, the A norm. You multiply it by this merging value. This is like safety factor. And you will obtain the design dimension, AD. This one, AD. So anyway, by introducing all this in your calculation model, analytical, numerical, anything you want, you can get these two, and you have to verify that this design effect of action is smaller than the design resistance. Okay. Normally, this is how it works. So during the development of Eurocode, there was much debate about the different form of this expression of ED, design effect of action, and design resistance. So in order to harmonize this, a Eurocode proposed is proposing 3 alternatives of design approaches. So each using different forms of the expression and sometimes different recommended partial factor value. It means that if you go from a country to another one, you will have different partial factors, the different value of partial factor. But Eurocode gave 3 design approaches. Okay. So this table here is giving us the 3 design approaches with the partial factors, as you can see here. So we have design approach 1, GA1, design approach 2, GA2, and design approach 3. Okay. So in this design approach 1, we have design approach 1, combination 1, and combination 2. 2 combinations for design action. Design approach, sorry, I'm saying design approach. Design approach 1, design approach 2, design approach 3. So in this design approach 1, we have 2 combinations possible. Combination 1 and combination 2. Okay. And for each of them, the value of these partial factors are given here. So partial factor on action, this is gamma F, or the effect of the action, gamma E. Okay. For example, if you have permanent and unfavorable action, then we call it gamma G. The symbol is G. If the action is permanent and is not favorable, favorable means a action that is not stabilizing, contributing for the stabilization of the structure. In that case, the action is G. But if the action is the G means here for the permanent action. Okay, the permanent action is G, but variable action like for example snow or wind, those actions are represented by Q. The accidental action by A. So if the action is favorable, then design approach, the combination 1 is saying that the partial factor should be 1.35. Combination 2 is saying 1. And you can see here is the action permanent and favorable. Here it's 1 and 1 here, and so on. You have this value. All these values are just the value for the partial factor. We have here a partial factor for soil parameter, means gamma M in the expression we saw before. Okay. Angle of sharing resistance, for example, you have gamma. That one is applied to the tangent of phi, for phi prime. So gamma tangent phi, the value are here. Cohesion, effect of cohesion, effective cohesion, the C prime. Okay, the gamma C prime. Undrained shear strength, Cu. Okay, the symbol is here, given by here. Unconfined strength, Qu. The symbol is gamma Qu, given the partial factor are here in each situation. Here is partial factors for the resistance. Resistance factor, gamma R. For example, for speed, spread foundation, retaining structure, and slopes. Okay, bearing resistance, sliding resistance, F resistance, or inclined slope. Each of them has symbol, its own symbol. Okay. Gamma RV, this is bearing resistance. Gamma RH, this is sliding resistance. Gamma RC, this is for the resistance of inclined slope. And we have the value of the incline of the partial factor in each design approach. Design approach 1, design approach 2, design approach 3. Okay. So for pile foundation, for example, or driven pile, you have this gamma R, base resistance, gamma B, self resistance, gamma S, total combined compression, gamma T, self intention, gamma ST. Okay, so the value are here for each design approach. It's a little bit complex, but once we start doing example, designing some example, you will see that it's not that complicated. Anyway, there are a lot of value. Each country has its own design approach, and some countries are even deciding that these value for partial factors are not suitable for them. They are using other partial factors. That's why here now the European Commission is trying, people who are working on the Eurocode 7, they are trying to investigate several ways to reduce and simplify the number of design approaches and design factors, national design partial factors. Okay. Now, anyway, the design approach one, this one, in this design approach, factors are applied to action alone in this combination one. Okay, you see, the combination one is the factor are applied here to the action only. You see, this action. And mainly to material, as you can see, material here, in this design approach one, combination one, we have partial factors applied to the action or effect of action, okay? But for material, it is just 1, 1, 1, 1, 1, 1. And you can see this star. This star means this partial factor, this partial material factor are used in this to avoid double factory. Okay. But in this design approach one, combination two, we can see here, mainly the factor are used for the material property. But here it mainly 1, 1, 1. Only this one is 1.5. Okay, because that one is not favorable action. In design approach 2, the factor are applied to action or effect of action and to the resistance at the same time. Okay, the same time we apply the partial factor on both. In design approach 3, the factor are applied to the structural action, but not to geotechnical action. And the material property also at the same time. Okay, structural action and geotechnical action. So according to this, to Eurocode 7, the way in which the equation for ultimate limit state for geotechnical and structure are applied, those weights shall be determined using one of these these three design approaches. Okay. You have to, every country has to use one of these three. So design approaches is applied only for this ultimate limit state. Don't forget, structure one and geotechnical one, limit state, ultimate limit state. Doesn't apply for others. Because we have seen that there are many ultimate limit state. We have uplift, we have equilibrium, okay, and the stability. And we have service also, service limit state, serviceability. So each country, each nation can choose which one or more to allow. Okay, you can choose each of these design approach is suitable for your country, or each of these partial factor are which of these partial factor are suitable for your country also. So each country has to choose. You can check the reference. So in Germany, for example, Germany decided that design approaches only apply to the geotechnical one, geotechnical ultimate limit state. For the structural one, that one is given to the structural engineers. It doesn't belong to geotechnical engineering. This is in Germany, for example. So speaking like this, we can say that the Eurocode is just completed by national annex. So in the Eurocode, the annex of the Eurocode, we have this part that they call national annex. So national annex will complete it like puzzle. You have the puzzle like this, and then each nation will come to complete this puzzle by its own chosen value, chosen data. Okay, we can have a non-contradictory complementary information from the country, national determined parameter you add. For example, if you take this value, not same for each country. Country specific data. Okay, some country, for example, have heavy snow, and though the other don't have. Some country have earthquake, some country don't have. So there are some data belong to specifically to the country. Okay, so there are some parameter or some method procedure to be used that the country can decide. For in our country, we use this procedure, guidance or information annex. So this is how the Eurocode will differ from one country to another. Okay, it's not same, but the principle of rules are almost same. There are some small detail that make it different from one country to another. Okay, so that's why if you go to Eurocode in this European country, maybe if you go to another country, European country, it will be a little bit different, but the difference will not be that much. There are some small details that make it different. Okay, for example, if we take this parameter, these are partial factors. The partial factor, for example, for slopes, in case of the material factor, we will talk about this. Okay, partial factor for soil parameter. Soil parameter, only this way, this one. Okay, so in case of the slope is drained, we have this line is the partial factor proposed by Eurocode. Okay, this one proposed by Eurocode. In case of a persistent action, we have this dark circle. Okay, and in case of transient action, we have this triangle, full triangle. Accidental action, high risk, medium, and low risk. So the value proposed by Eurocode for this gamma phi is this one, tangent phi actually. Gamma C is this. In case of in case of drain slope is gamma C. Okay, these two, for example, the value proposed by Eurocode. But if you go in Sweden, for example, they are using this value instead of, as you can see here we can say that it's 1.25, right? 1.25, for example. Okay, 1.25. And you can see here, this table is from Eurocode. Okay, so you can see 1.25 in gamma phi. This is Eurocode. And in Sweden, they're using 1.3, for example. Okay, for this gamma C and gamma phi. Eurocode is both. You see gamma C and gamma phi, both are 1.25, 1.25 when it is applied. In Germany, for example, they are using 1.1 for accidental and maybe 1.15 for this transient one. In Portugal, we have this. In Denmark, we have this. So Netherlands, we have this. It means that even these partial factors, if you go from one country to another, they are sometimes different. But some countries are using exactly the value proposed by Eurocode. This is when the slope is drained. When the slope is undrained, in that case, we have this CU and QU, the undrained shear strength and the undrained strength. Okay, the unconfined strength. So Eurocode is proposing 1.4. You can see 1.4 here, 1.4, this line of Eurocode. Some country, like for example, Greece, are using the value proposed by Eurocode. Okay, and also I think Portugal, in some cases, persistent and transient. But Portugal, for in case of accidental, they're using this value. Okay, so it is not same when you change from a country to another. So another example is this following figure about the design approach. So we have 3 design approaches. So each country is using different approach. Okay, for example, for slope, the same slope again, we have this, for example, a map. The red part here and here, this country are using design approach 1. We have 3 design approaches. This map is about the design approach used for by each country when it comes to slope stability. Okay, so design approach 2, for example, this country. Design approach 3, the green one, Norway, Sweden, Finland, Denmark, Germany, Poland, this kind of country, Netherlands. Spain. Design approach 1 and 2 are used, for example, in Italy. Okay. Design approach 2 and 3 are used, for example, in France. Design approach 1 or 2 or 3 are used, for example, Iceland, okay, Czech Republic. But some also are unknown, like this. That was for slope stability. This one is for shallow foundation. Shallow foundation, you can see that it's different. The color is changing. Okay, the color code is showing which country is using which design approach from within the three design approaches. Okay, if for example we go from slope 1, let me go back here to the shallow foundation. You can see how the color is changing. Okay, slope, shallow foundation, slope, shallow foundation. For example, if we take UK, United Kingdom, they're using only one design approach. The design approach 1. Only one is used, design approach 1. Okay, same color. Okay. If you take, for example, Germany, you can see that for shallow foundation, they're using, the color here is telling us design approach 2. If we take slope, color is green. So for slope, they are using design approach 3. This is in Germany, for example. You can take example of on any country, Spain, Portugal, Italy, Romania, everywhere. Okay, shallow foundation. And if we go in case of deep foundation, 5, for example, each country is also using different design approach. Okay, so let's talk now about the limit state equilibrium limit state. How we verify the equilibrium limit state. Verification of this static equilibrium is expressed by this formula. Okay, we have E dst, and D should be much less than the ESTB. I think I have explained this before. The stabilizing action effect and stabilizing action effect. Okay, so this one, the destabilizing design value of effect of this destabilizing actions, and this one is, in contrary, the design value of effect of stabilizing action. And this TD is the design value of stabilizing shear resistance of the ground or the structural element. Okay, so to check the stability, we should make sure that this left side is much less than the right side. And this one is used for equilibrium, loss of equilibrium of structure, or the ground is considered as rigid body in which the strength of structure, material, and the ground are significant in providing resistance. So for this equilibrium, you can, from this equation, you can check the equilibrium. Don't worry, we will take some example on this one, and you will see that it's not that difficult. Let's go now for the service limit state. The verification of serviceability is expressed by this equation. So ED should be less than CD. The ED is design effect of action, displacement, distortion, bending moment. So these are the effect of action. Okay, those should be less than design content, limiting value of design effect. Okay, for example, displacement should be less than this, settlement should be less than this amount, this, something like this. So just The service limit state is very easy. Just checking this. If bending moment is less than a certain amount, then it's okay. The service limit state is okay. So this is according to this Eurocode 1990. The partial factor should normally be taken in equal to 1. We should not increase them or decrease them. Okay, this is all for this. Sorry, it was a little bit longer than usual, but I wanted to finish everything about the action, about the limit state, so that the next time we will go for the following point in this chapter. Maybe we finish maybe 2 more video on this, at least 2 more video on this chapter before we complete the chapter. Okay. Thank you very much for your time and see you next time. Thank you.